Mm. Hello, everyone. Our topic for today is going to be NoSQL databases, which are becoming essential in modern data-driven applications. Unlike traditional SQL databases, NoSQL databases are more flexible and scalable. They handle diverse types of data and can support large volumes of information distributed across multiple servers. Over the next few slides, I'll explain the core concepts, technical details, and real-world applications of NoSQL databases. We'll cover four major types. First, document-oriented. Secondly, key value. Third, columnar. And finally, graph databases. Each has unique strengths and is optimized for specific use cases. And by the end of this video, hopefully you'll have a solid understanding of what NoSQL's databases are and why they are used. Now let's start with a brief introduction about NoSQL databases. NoSQL databases are non-relational databases designed for handling large volumes of distributed data. People often prefer to use NoSQL because they are suitable for unstructured or semi-structured data. In addition to their high scalability, high flexibility, and amazing performance. NoSQL versus SQL. NoSQL focuses on high availability and scalability, while SQL emphasizes structured data and complex queries. Let's start with a brief history of NoSQL. They emerged in the early 2000s as a response to the growing demand for handling web-scale data. Companies like Google, Amazon, and Facebook needed new ways to store and manage massive amounts of unstructured data. Traditionally, relational databases were too rigid and couldn't scale horizontally across multiple servers. This led to the development of distributed schema-less databases that we now call NoSQL. In fact, Amazon's DynamoDB and Google's Bigtable are some of the earliest examples of NoSQL databases. These companies were pioneers in building systems that could handle large volumes of data with high availability and fault tolerance. Now, here are the core principles of NoSQL databases. They are built on four core principles. First one is schemaless. There's no fixed table structure. You can store different types of data without defining a schema beforehand. Secondly, distributed. Data is spread across multiple servers, ensuring high availability. Thirdly, their high availability. These databases are designed to remain operational even if some servers fail. And the last core principle is horizontal scalability. You can add more servers to handle increased data instead of upgrading your existing hardware. For example, you can add several more servers to handle the data load instead of updating your already existing hardware, which needs more money and is more expensive. These principles make NoSQL databases ideal for applications that require constant uptime, such as e-commerce, websites, social networks, and streaming platforms. Types of NoSQL databases. There are four main types of NoSQL databases, each designed for specific use cases. First type is document-oriented databases. It stores data in JSON-like documents, and MongoDB is a popular example. Secondly, key value stores uses a simple key value pair model. Redis is widely used for caching and session management. Thirdly, columnar databases stores data in columns instead of rows. Apache Cassandra is a leading columnar database. And finally, graph databases. It focuses on relationships between data points. NEO4j is the most popular graph database. Each of these types addresses specific data storage needs. Now, let's firstly start with document-oriented databases. The definition, they store data as JSON-like documents, making them highly flexible. MongoDB is one of the most popular document-oriented databases. Each document contains key value pairs, and documents are then grouped into collections. The key advantage of this type of database is its ability to handle diverse data structures without requiring a predefined scheme. For example, let me give you an example. For instance, a user profile document in MongoDB might look like name, year, age. These structures allow you to store different types of information in a single document, making it ideal for content management systems, e-commerce platforms, and real-time analytics. MongoDB has several key technical features. First of all, the data model. It uses collections to group related documents. Secondly, its indexes. MongoDB supports indexing to improve query performance. Thirdly, replication. It ensures high availability through replica sets. So it creates sets of replicas to ensure the availability that is always available. Fourthly, sharding. MongoDB can distribute large data sets across multiple servers. This is called sharding, and this improves the scalability. And finally, we have the aggregation framework. It allows you to perform complex data processing directly within the same database. Now, here is an example of the MongoDB code. And some common use cases for MongoDB include content management systems, easily manage diverse content types. Secondly, real-time analytics, process and analyze data as it comes in. And finally, e-commerce platforms. Sort product catalogs within varying attributes. Now here is the example, as you can see here in the second line of the code MongoDB uses. Now here, let's dive into the second example, key value stores. Key value stores are among the simplest types of NoSQL databases. They store data as a collection of key value pairs where each key is unique. One of the most popular key value pairs store is Redis. Redis is known for its incredible speed because it stores data in memory. This makes it perfect for real-time applications that require low latency response, such as caching, session management, and real-time analytics. For example, if you're on a website, you can use Redis to cache frequently accessed data. This reduces the load on your main database and speeding up your website's response time. Now here are some advanced Redis features. Redis offers several advanced features. For example, its persistence. It supports RDB and AOF for data durability. Replication, and secondly, replication. It is a master-slave replication for high availability. Thirdly, pub or sub. It is a real-time messaging system. And fourthly, transactions. Support atomic operations to ensure data consistency. And finally, we have the Lua scripting. It allows you to execute several side scripts for advanced functionality. All these are advanced features provided to you by Redis. Now here are Redis examples. Here's an example of how Redis is used for session management in web applications. You can set a session key for a user with a command like set session user. Here we have activated the session key. And then you want to check if the user is active. You can use the command get, as you can see here, get session user active to check if the user is active. And if it's active, it will return active. This quick lookup makes Redis ideal for managing user sessions for high traffic websites and also demonstrates fast data retrieval. Let's now look at columnar databases, specifically Apache Cassandra. Unlike traditional databases that store data in rows, Cassandra stores data in columns. This makes it ideal for handling write-heavy workloads. Columnar databases are particularly useful for time series data, where we need to record events over time, such as IoT sensor readings or financial transactions. One key feature of Cassandra is that it offers high availability with no single point of failure. Even if one node goes down, your data remains accessible from all other nodes in the cluster. Now here are some of Cassandra's technical features. We have the first feature is partitioning. Data is distributed across nodes using consistent hashing. This ensures even distribution and load balancing. Secondly, we have replications. It ensures Cassandra uses replication to ensure data redundancy and fault tolerance. You can configure how many copies of your data are stored. Thirdly, we have the CQL, Cassandra Query Language. It is an SQL-like language, but it is used for queries. This makes it easier to interact with Cassandra. Fourthly, we have the consistency levels, tunable consistency for availability, meaning you can adjust consistency levels to balance between strong consistency and high availability. And finally, we have scalability. Cassandra can handle massive data sets by adding more nodes to the cluster without downtime. So let me give you an example on these technical features. For example, a company is tracking IoT sensor data. It can use Cassandra to store readings from millions of devices in real time, ensuring that data is always available and consistent. Using these four features, these five features, it ensures that data is always available and is always consistent. Here, Cassandra. Here's an example on Cassandra. Here's an example on the code used by Cassandra. And Cassandra is most commonly used in the following scenarios: either IoT applications, or time series, or logging systems. Companies like Netflix and Spotify use Cassandra to manage large-scale user data across multiple locations. Now let's move on to graph databases. NEO4J is a leading graph database that focuses on relationships between data points. In graph databases, data is stored as nodes, relationships, and properties. Nodes represent entities, relationships, nodes, each node represents an entity, and the relationships between them connect each node with the other. And properties store additional information about the node or the relationship. This structure makes graph databases perfect for applications where understanding relationships is crucial, such as social network, recommendation engines, and fraud detection. Now here is Cypher query language in NEO4J. NEO4J uses a query language called Cypher, which is specifically designed for graph databases. Cypher is intuitive and resembles natural language, making it easy to write complex graph queries. For example, you can create nodes and relationships with the following Cypher command. Create in person, name Alice, age. This command creates a person named Alice with an age of 25. And then you can match it with the other person. The use cases for NEO4J or graphical databases, it's shortest path queries or cycle detection. So NEO4J is widely used in social networks. It is used to analyze user connections and interactions, and it's also very commonly used in recommendation engines to suggest products or content based on user behavior. And finally, they are used for fraud detection to identify suspicious patterns and relationships in financial transactions. Now here we have the CAP theorem in NoSQL databases. The CAP theorem is a fundamental concept in distributed systems, including NoSQL. It states that a distributed database can only guarantee two out of three properties at any given time. So CAP stands for consistency, availability, partition tolerance. Consistency means all nodes see the same data at the same time. Availability means every request receives a response, even if some nodes are down. And finally, partition tolerance. The system continues to operate despite network patterns. So the CAP theorem states that each system must have two out of these three. So this makes them highly available and fault tolerant. Now here's a quick comparison of NoSQL databases. These are the four types that we have already discussed. Document-oriented. So as you can see here, document-oriented, example for it is MongoDB. The its use cases and its key features. So we have the document-oriented. This is a flexible schema suitable for content management systems. Here we have the key value. It's fast memory storages and ideal for caching and session management. Thirdly, columnar. It is an example of it is Cassandra. It is very useful in IoT or time series data, and its key features are it is distributed. Its key features are it's scalable and distributed. And finally, we have the graph. Graph focuses on relationships, perfect for social networks and fraud detection. Now here, while NoSQL databases offer many advantages, they also come with challenges. The first challenge is data consistency. Data consistency. Achieving consistency can be difficult in distributed systems. Secondly, is complex querying. Not all SQL databases support advanced querying like SQL. Thirdly, is learning curve. Developers need to learn new concepts and query language. Despite these challenges, the benefits of scalability, flexibility, and high performance often outweigh these drawbacks. So these drawbacks are not really crucial when you have many other advantages that are more important and more important in use in the future. Here are the future trends in NoSQL databases. Now looking ahead, here are some key trends in the NoSQL space. The first key future trend might be the multi-model databases that support multiple data models within a single system. Secondly, the integration. You can integrate it with AI or machine learning. NoSQL databases are increasingly being used in AI and machine learning application to store and process large data sets. This leverages NoSQL databases. Thirdly, we have the serverless database. These are managed services that automatically scale and handle infrastructure, reducing operational overhead. The future of NoSQL is about combining flexibility with intelligence, making it easier to store, query, and analyze complex data. Now here finally, to wrap up, NoSQL databases offer powerful solutions for managing modern large-scale applications. They provide flexibility, scalability, and high availability. Each type of NoSQL